Hello everyone. Today we are going to see about three-phase induction motors. In this lecture, we will see why induction motors are so widely used, how they are classified, what rotating magnetic field is, the basic principles of operation, how speed and splits are defined, and finally, how the induction motor related to the transformer and what their main limitations are. Three-phase induction motors are most common and most friendly encountered electrical machines in industry. They are popular because their simple design, rugged construction, relatively low price, and easy maintenance. L. These motors are wide range of power ratings from small fractional horsepower motors up to machines of order of 10 megawatts. The speed of an induction motor depends mainly on frequency of the power source, which means its speed is essentially tied to the supply frequency. Because of this dependence, varying the speed is not straightforward with a fixed frequency supply. For good variable speed control, induction motors require a variable frequency power electronic drive. There are several reasons why three-phase induction motors are preferred in many applications. They are robust machines with no brushes, no sliding contacts on the rotor shaft, which improves reliability and reduces maintenance. They have high power to weight ratio compared to DC motors. So far, the same output power in the induction motor can be more compact. They also offer lower cost per unit power, are easier to manufacture, and are almost maintenance free apart from bearings and other mechanical parts. Classification of motors. In general, motors can be classified in several ways, such as DC motors and AC motors. And under AC motors, we have synchronous motors and induction motors. Within induction motors, the two main types are squirrel cage and wound rotor induction motor. Now we come to the key idea, the rotating magnetic field rotating magnetic field. In a three-phase stator, the windings are placed 120-degree apart around the stator and are supplied by the balanced three-phase voltage source. When these balanced three-phase current flow through the stator winding, they produce three magnetic fluxes in space that are also 120-degree apart in time. The combination of these three time shifted fluxes produces a magnetic field of constant magnetic that appears to rotate around the gap. The speed of rotating magnetic field is called the synchronous speed, and it depends on the supply frequency and the number of poles of the machine. The synchronous speed in revolution per minute is given by the well-known formula sync is equal to 120 divided by F, 120 F divided by P, 120 F where F is the frequency in hertz, P is the number of poles. These values are useful for quickly estimating approximate speed of an induction motor for a given supply frequency and pole number. How induction motor works. Once the rotating magnetic field is established in a air gap, it cuts rotating conductors. This changing flux linkage induces a voltage in a rotor windings according to Faraday's law. In both squirrel cage and wound rotor induction motor, the rotor windings are effectively short-circuited so that induction motor voltage drives a current through the rotor bars or windings, and this rotor current in turn produces own magnetic field. A torque is produced due to interaction between stator magnetic field and the rotor magnetic field. So this is the equation we have generated while we are considering the rotating magnetic field. So this is the principles of operation which we see earlier. Now a natural question is, at what speed will the induction motor actually run? Can it run exactly at synchronous speed? If the rotor were to run at synchronous speed, the rotor conductors would feel a stationary magnetic field with no relative motion between the field and the rotor. In that case, the rotating magnetic field would no longer cut the rotor contacts. No induced voltage would appear in the rotor, no rotor current would flow, no torque would be produced. As a result, the rotor speed would drop below synchronous speed again, restoring some relative motion, induced voltage, rotor current, and torque. This shows that in steady state, a three-phase induction motor always run at a speed slightly less than synchronous speed. The difference between the synchronous speed and the actual rotor speed is called slip speed. So it is denoted in the equation S is equal to N synchronous minus Nm divided by N synchronous. So S is a slip. So if the rotor runs at synchronous speed S is equal to 0, the rotor runs stationary S is equal to 1. Typical operating slip values of an induction motor at rated load are small, usually few percent, which means the rotor speed is very close to synchronous speed but always little lower. There is strong analogy between an induction motor and a transformer. Both operate based on the principle induced voltage in coupled windings. In a transformer, voltage applied to the primary winding produces an induced voltage in a secondary winding, with both windings being stationary. In an induction motor, voltage applied to the stator winding produces an induced voltage in rotor winding, but here secondary, the rotor is free to rotate. Because of the rotor rotating, the frequency of induced voltage and current in a rotor is not the same as the stator frequency. It depends on slip. This is the important difference between a transformer and an induction motor. The main limitation of the standard induction motor is that it is essentially a fixed speed machine when supplied from a constant frequency source. Machine when supplied from a constant frequency source, its speed mainly determined by the supply frequency and the number of volts with only a small variation due to slip. To vary its speed over wide range in an efficient way, a variable frequency supply is required, which is provided by power running drives such as inverters. With modern drives, however, induction motor can now be used in many variable speed applications as well. So these are the references. To summarize, three-phase induction motor widely used in industry because they are simple, rapid, low cost, and require little maintenance. They work by creating rotating magnetic field in the stator, inducing current in a rotor, and producing torque due to interaction of a stator and rotor fields. The rotor speed is always slightly less than synchronous speed, and this difference is quantified by the slip. Thank you.